this video, we're going to talk about solids and its properties. The learning competency for this video is to describe the difference between the two, and the specific learning outcome is to compare the properties of crystalline and amorphous solids. The solid state is distinguished from gas and liquid states by a rigid structure in which the component atoms, ions, or molecules are usually locked into place. In many solids, the components are arranged in extended three-dimensional patterns, producing a wide range of properties that can often be tailored to specific function. Thus, a diamond, an allotrope of elemental carbon, is one of the hardest materials known, yet graphite, another allotrope of carbon, is a soft, slippery material used in pencil lead and as lubricant. Therefore, when we discuss solids, we consider the positions of the atoms, molecules, or ions, which are essentially fixed in space rather than their motions, which are important in liquids and gases. So the constituents of a solid can be arranged in two general ways. They can form a regular repeating three-dimensional structure called a crystal lattice, thus producing a crystalline solid, or they can aggregate with no particular order, in which case they form an amorphous solid. So it's from the Greek word amorphos, meaning shapeless. Now, the differences in properties of these two groups arise from the presence or absence of long-range order of arrangements in the solid. So what are the differences? Crystalline solids are arranged in fixed geometric patterns or lattices. Examples are ice and sodium chloride. Other examples include copper sulfate, diamond, graphite, and sugar. Now, the ordered arrangement of their units maximizes the space they occupy and are essentially incompressible. Amorphous solids, on the other hand, have a random orientation of particles. Examples include glass, plastic, coal, and rubber. So they are considered supercooled liquids where molecules are arranged in a random manner similar to the liquid state. Now, more than 90% of naturally occurring and artificially prepared solids are crystalline. Minerals, sand, clay all have crystalline structures. Now, the repetition of structural units of the substance over long atomic distances is referred to as long-range order. Okay, so amorphous solids such as glass are like liquids. They do not have long-range order but have limited localized order in their structure. So the presence or absence of long-range order in the structure of solids results in a difference in the behavior of the solid when heated. Okay, so as I have said, the structures of crystalline solids are built from repeating units called crystal lattices. The surroundings of particles in the structure are uniform, and attractive forces experienced by the particles are of similar types and strengths. So these attractive forces are broken by the same amount of energy, and thus crystals become liquids at a specific temperature, which what we call the melting point. At the melting point, physical properties of the crystalline solids change sharply. Examples are pyrite or the fool's gold or fluorite. Okay. Now, amorphous solids, they soften gradually when they are heated. They have the tendency to melt over a wide range of temperature. This behavior is a result of the variation in the arrangement of particles in their structures, causing some parts of the solid to melt ahead of other parts. This behavior is noticeable in substances such as coal and plastics, which are both amorphous solids. So I want to start this discussion with the amorphous solids because it's easier and less tedious than crystalline solids. Amorphous solids lack regular arrangement of atoms. So we say that the molecules in an amorphous solid are arranged in a random motion or manner. and that we say that this kind of solid has no long-range order. Amorphous solids also do not diffract. Glass is a familiar and important amorphous solid. They are optically transparent fusion product of inorganic materials that has cooled to a rigid state without crystallization. So glasses are composed mainly by mixing molten silicon dioxide with other components such as sodium oxide, boric anhydride, and certain transition metal oxides. So they behave more as a liquid than a solid. Now this figure shows a crystalline silicon dioxide, or what we call quartz. Just by observation, you will already know the difference between amorphous silicon dioxide and crystalline silicon dioxide. So what are the distinguishing feature of crystalline solids? To answer that, we have to further talk about the crystal lattice. You have to remember that the lattice structure of a crystal solid depends on the nature and size of the particles involved. It also depends on the intramolecular and intermolecular forces present. To be specific, the forces responsible for the stability of crystalline solids are the following. We have ionic forces, covalent bonds, van der Waals forces, and hydrogen bonds, or a combination of some of them. Now, I have mentioned crystal lattice a lot of times, but what exactly is a crystal lattice? Keep in mind that each crystalline solid is represented by a crystal lattice. Now think of crystalline solid as this Rubik's Cube, okay? So this Rubik's Cube is made up of smaller cubes connected to each other. Each cube is what we call a unit cell. Now, the arrangement or structure of these connected cells or cubes is what we call a crystal lattice. So basically, the crystal lattice is like a scaffolding for the solid. Okay? Now, the unit cell is the fundamental concept in solid state chemistry. It is the smallest representation of structure which carries all the information necessary to construct an ambiguously infinite lattice. Okay, on a molecular level, it looks like this. So the edge of each unit is what we call a lattice point. At the lattice point, you can see the atoms, the molecules, or ions. So this one is a cubic cell and it is the simplest unit cell and has structural particles centered only at its corners. So if you're going to look at this figure, there are seven fundamentally different kinds of unit cells, which differ in the relative lengths of the edges, which are indicated by A, B, and C, and the angles between them. So alpha is the angle between B and C, beta is the angle between A and C, and gamma is the angle between A and B. So each unit cell has six sides, and each side is a parallelogram. So we focus primarily on the cubic unit cells, in which all sides have the same length and all angles are 90 degrees. But the concepts that we introduce also apply to the substances whose unit cells are not cubic. Okay? So the way atoms are arranged to form an ordered three-dimensional structure is called packing. Okay? Remember that the type of unit cell is determined by the way atoms are packed or arranged in layers. So we have two kinds of packing, the open packing and the closed packing. By observation, you will see that the open packing has larger voids in between particles compared to closed packed crystals. Now, in some books or references, they call open packing as square packing because if you notice, you will have 4 points touching here. One, two, three, four. Okay? And they call close packing as hexagonal stacking because you have 6 points. Okay, so you're touching 6 other atoms. 4, 5, 6. So we have three types of cubic unit cells as shown in this figure. We have primitive cubic, body-centered cubic, and face-centered cubic. It's a primitive cubic when the lattice points are at the corners only. It is a body-centered cubic or BCC when the lattice point also occurs at the center of the unit cell. Now it will be called as face-centered cubic or FCC when the cell has lattice points at the center of each face as well as at each corner. To make it easier to visualize, I will show you a video from the user Yusuf Nasihi. So he makes chemistry, physics, and other scientific videos. So if you want, you may check his YouTube channel. The video that you will see will discuss the types of cubic cell. The video that the video that you will see will discuss the types of cubic unit cells and their origins. Okay?
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above, and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell.
Okay, so again, from the video, you have seen the concept of coordination number. Coordination number is the number of atoms or particles surrounding an atom in a crystal lattice, or simply the number of atoms touching it. So coordination numbers indicate how tightly the atoms pack. The larger the coordination numbers, the tighter the packing is. So face-centered cubic here has 12, right? So now let's talk about the close-packed lattices in 3D. So close-packed lattices allow the maximum amount of interaction between atoms. So if these interactions are mainly attractive, then close packing usually leads to a more energetically stable structure. As we pointed a while ago, hexagonal packing of a single layer is more efficient than square packing. So this is where we begin. In the first layer, the spheres are arranged in a hexagonal pattern where each sphere is being surrounded by 6 others. Okay, so we call it layer A. Then, a second layer B with the same structure is added, but the layer is slightly shifted, hence just filling the gaps of the first layer. Now, in a third step, another equivalent layer is added, filling the gaps just as before. But now there are 2 opportunities. Either this layer lies exactly above the first one, or so layer A again. So we'll have a pattern ABA, or it is shifted with respect to both A and B and thus has its own position C. So we will have the pattern CPA. This ABA pattern is called the hexagonal closest packing, or HCP, while this CBA or ABC pattern is called FCC, or the face-centered cubic, or some references they call it CCP, cubic closest packing. So let's have a closer view. This one. So a CCP arrangement has a total of 4 spheres per unit cell. Okay, so a CCP arrangement or a FCC arrangement has a total of 4 spheres per unit cell, and an HCP arrangement has 8 spheres per unit cell. However, both configurations have coordination number of 12. So why is it important to know all of these? What's the importance of the packing? The arrangement of atoms in a crystalline solid affects atomic coordination numbers, interatomic distances, and the types and strengths of bonding that occur within a solid. So, an understanding of atomic packing in a unit cell and crystal lattice can give insight to the physical, chemical, electrical, and mechanical properties of a given crystalline material. Now, we're not going to talk about the relationship between the edge length and atomic radius. So that would be for another topic and for your higher chemistry. So how are the structures of crystals determined? Structures of crystals are determined by X-ray diffraction. X-ray diffraction is a technique used to determine the atomic and molecular structure of a crystal, wherein atoms cause beams of incident X-rays to diffract into many specific directions. Here is an image of a diffraction pattern produced by an electron beam incident on graphite crystal. So how does this work? Okay, so first a sample is powdered and it is placed here. Then X-rays of single wavelength is used. So from the X-ray tube, it will pass a lead screen. Then this beam will hit the crystal sample, diffracting it. It means that the wave scatters in an elastic manner. So we call it elastic scattering. This is a type of scattering where the wave interacting with a particle bounces off in some direction without changing its wavelength. So this will produce patterns or spots from diffracted X-ray. Okay? Now this big circle in the middle is a spot from the incident beam. That's why you have here the shield. Okay, so the distance between planes of atoms in the crystals are calculated from the angles at which the rays are diffracted using Bragg equation. Okay, so here you have two layers. Okay, layer 1 and layer 2. Okay, so the incident ray 1 will hit atom A and be reflected at a certain angle. So this reflected ray will be measured by an X-ray detector. Okay? So and this incident ray 2 will hit atom C. Then it will be reflected. Okay? But if you notice in this figure, incident rays 1 and 2 have different path lengths. Okay? They are only the same at this point, from A to B, and in terms of reflected rays, it's the same from A to D. Okay, so you have some extra distance. To get the length of the extra distances, we need to use some trigonometry concepts. So from A to C, this will be your hypotenuse D. Okay, and you will have right angles here, here, and angle here, theta. So to get the distance from B to C, you will have d sine theta, and from C to D, you will have d sine theta. So the extra distance traveled by the lower ray is equal to BC plus CD, which is equal to n times lambda, where n is an integer and lambda is the wavelength of the X-rays. So this will be equal to 2d sine theta. Okay, so this is what we call the Bragg equation. Now I'm going to leave the solving part to your higher chem subjects, but this is one of the ways to derive Bragg equation. This figure shows one of the first X-ray diffraction photographs. So the figure on the left is one of the first X-ray diffraction photograph, and on the right is a modern X-ray diffraction projection. Okay, so in the next video, we're going to talk about the types of crystals.